Hello everyone, we're back to the next section, Roadshow. Our Roadshow will begin soon after 10 minutes. Yeah. So please take your cell phone into the silent mode, and there are also so many empty in the front row, so you can go take a seat in the front row.
I've started my computer programming journey when I was a junior high, and my first aim was to win gold in IOI. Then when I entered university, my goal was to win gold in ICPC.
I think I've started competitive programming at around 2011. I won ICPC World Finals in 2018 and 2019.
参加这个 UCup 对我算法竞赛有很大的正面影响，感觉题目质量都比较高。
小学的时候用那个 Scratch 编一点东西，觉得电脑很好玩，想要干点这个，然后就选了一个有这个信息竞赛的中学去上，然后就开始这。
And I started doing them actually quite a while ago, which is 15 years already.
I'm the youngest. I'm doing competitive programming for 11 years. At some point you come across a branch of math, which is programming, and you decide that it's interesting, it's nice, you try it, and maybe you discover that you are good at it.
I've been doing competitive programming for quite a while now, since I was 7 or 8 years old. I started mostly because my parents are programmers and they just felt like, I mean, I was probably good at math, but I wasn't doing math Olympiads, of course, but they decided that I can try and see what goes.
I started competitive programming in my 3rd grade of the high school. I study statistics at my university, and I have interest in finance, so in my future, I will study about finance more than programming, but I like to do competitive programming because puzzle and mathematical things of this is very fun.
接触算法竞赛大概就是初一的时候吧，就开始写游戏，然后就顺便学了学编程。
I think ICPC teaches you how to solve problems in general, like problem solving skills, and also how to do things fast, even if, for example, you're doing coding interview or just doing work at work. It actually, I think, indirectly helps you, and I think I observed some cases where I think people could have benefit from having some sort of background like I have.
Yeah, and I do think that competitive programming experience helps you to like go to faster, to like create some like starting point, to like create some code quickly and to get it working. Also, it helps you to be like more careful with like some corner cases, because you in competitive programming you want your code to like always work on all test cases.
I just enjoy problems. Of course, I enjoy winning, but even if I can't win, I still can enjoy computer programming. So I'm involved in this community.
One definitely important thing is that competitive programming problems are challenging, and they are like being progressively better at them. I think performing under pressure is another factor that can become important in life at various points.
And I think it's generally competitive programming experience is rather useful for high frequency trading, because like you want to test a lot of ideas and you want to do it quickly, and that's precisely what is like really good, what competitive programming trains you to do.
就我觉得我从竞赛中学到一个教训，就是其实有的时候合作非常非常重要，就是你和人聊一聊什么，其实对你会非常有启发。
Pure joy of solving just problems and work in the team. So now it's an on-site event. I'm really happy to be here, because usually even in a team, we participate in contests remotely, and it's not the same experience.
But anyway, I think a lot of engineering skills indeed, like there's a lot to gain, and especially like if you are looking for like different ways to do it, like I think you can learn a lot from other people. And for example, often when you do competitions, you can learn the approaches of other people, or like how they handle their like code or like ideas, and that's very valuable.
I will just stay close to just theoretical research.
I'm now working on Kotlin programming language compiler. I'm quite happy with what I'm doing and don't have any plans for big changes.
I did a research maths degree just right after my ICPC last event, so that possibility to return to, I didn't get a PhD.
就是做理论计算机，经常想题，挺有意思的。
然后读人工智能的专业对口的博士，对，我做的是可解释性方向，也是读人工智能方向的 PhD， 对，然后做的我也不知道做什么，可能还在探索。对，但我也很想造出来更聪明的模型。
Well, I work in physics. I'm an experimental physicist.
I am a bachelor student, and right now I really want to keep studying and pursue a master's degree and maybe something even further.
我未来计划继续打 ICPC， 就是这方面的竞赛，争取能到 World Final， 然后我也会继续练习。
For me personally, it would be cool to be on the cutting edge of technology.
Hello everyone, welcome back to the 2026 Universal Cup Final Challenge. There is the Roadshow section, and please take your seats as soon as possible. Please take your seat. Okay, I'm Li Mingzhen from Huawei context management departments. In this section, I will welcome some. I will invite some team that had participants the challenge contest to share their idea, their code, or their other extra information about this challenge problem. Share how to solve it, how they are thinking, and in this computer, you can use this computer to share the code that you have submitted during the competition. For example, like this, and of course you can use this pad to not annotate. Yes, like this. You can use it to annotate. Okay, so we are ready. So let's begin. And the first team is the Doves Proactives Virtual. Where are you? Are you here? Dot Proactives Virtual, the team. Okay, welcome. You need to use mics or this mic. You need to use this mic or this mic.
I would rather use this one.
No, you can use this. You can share the code.
I don't remember which one is the okay. Yes, thank you. Okay, thank you. Okay, so we started with pretty easy solutions that actually I think replicated the baseline. Let me see. Yeah, and well, our function for scheduling were pretty slow. Can schedule work it in linear time. It was pretty slow. It got a lot of time limits, so we changed it to segment tree, which is still pretty slow. And that's how we got lucky that this one was pretty slow, because it was pretty slow, we come up with idea. What if we wouldn't try each current task for each GPU at each second? And instead, what if we will stop trying after we get like some number of rejects? And that's how we got our first submission over 360 million. But just skipping after first 20 times that we couldn't find a place for a request. Then we just fiddled with a sorting function. For example, here we sorted by 2 times LE plus LOut times LOut. In the end, we used 3 times LI plus 2 times LOut times LOut, and we changed our skips to 35, I think, and that was ideal. That's all.
Please, hello, please keep. Anyone will have some question or discuss with him? Okay, I have question. Sorry, I have questions. It seems that most of the teams have used the language C++, but you use the Rust.
Yes.
Why?
Well, me and Boris both use Rust in our competitive programming.
Okay, just familiar.
So we just use Rust because of that.
Okay, okay, thank you, thank you. Okay, just take a seat. Okay. Now invite the next teams. Let me check. The next team is Arvin and Arrow game. Arvin and Arrow game. Let's welcome. You need to take this phone or this one. Okay. Yeah, you can use this one to annotate.
Annotate? This way. No, I think it's like a pencil. Oh.
There is a pencil. There is. There is a pencil.
Wait, I think you should talk about how you optimize the baseline first.
Yeah. Okay, so the first thing we did is try to implement the baseline. I'm not sure if I can. Okay, this is my typical timetable, which has nothing to do with the problem. Right, so we implemented the baseline, and then the most obvious solution is just maintain a like 6 billion integer array for each GPU. That was quite slow, so we use a different method. For each GPU, we store all the actual events, and then we do a linear brute forces, and that was fast enough to pass the test. Even though it's like not very optimized, but I think in a like 5-hour contest, it's like good enough, fast enough for our purpose, right? So that's the first thing, and then the second. And then the second thing is we realize we don't really have much good ideas, so we look at how the baseline, like how many places in the baseline that we can like change. And I realized I think we really have 2 places to change, which we can put. Right, so there are 2 choices. There are 2 things we can do. What is a GPU choice, which is okay, the baseline is smallest index, and we can see that we have a few options. Take a random, take a like counting by minimum schedule something. Okay, and the second very important option is sorting. It's about how we prioritize tasks to sort to use, right? So we just experimented with a lot of options of how to sort what's the value of priority given to each of the tasks. So okay, here's like the configurations. We have like a few parameters. We're going to write the formula out, and then we can just optimize all the parameters here. Right. Okay. So, so after we know that, we realize that for different kind of parameters, they do on different tests, on the very different tests. So we just like invent a strategy to like find out which case is it, and then we do some offline data analysis to take all the performance of each configuration, and then we just use the best configuration of each of the test cases, right? We end up using like. The screen isn't updating. You can use this back to. Oh, okay. Right, so we hard-coded some of the hashes, and then hard-coded which strategy is the best. We have end up using like 10 to 20 strategies here. Those are here, like, right. So, for example, like alpha 0.1, we tune one of the alpha's values, and then and a few choices. Okay, this is all 100 of them. Anyways, yeah, this we did this in Python in pandas. So, yeah.
You might be wondering, how do we get the hash of the test case? Apparently, you can do exit program, and it prints the exit number. So this gives you like 8 bits. So we did that twice, and we got 16 bits, and this was enough to like separate almost all test cases. Also, there might be a bug with the testing, because like we use Kotlin, and we had 14-second time limit. So like we might have like got more points from like 14-second time limit. Unfortunately, we are not very smart because like there's better sorting algorithms because we use like only linear terms, but apparently like this is very strong. Like, oh wait, can I annotate? Like, apparently, oh, wait, what? Wait, 这个怎么用？直接可以用啊，直接可以用的。哎，点这个，然后可以用。Okay, like apparently this sorting is very good, but we didn't try it because you're not very smart. Apparently, like, so if you set alpha equals 0.2 and beta equals 1, like this is just the area of like the tokens you use. But apparently a very good strategy, like a very like good strategy was apparently this. Like some other team told us that, but yeah. But it was just like trained on test hyperparameters. Yeah.
Okay, anyone has question to the? Anyone has question? Okay, I have a question because you are in another team. They did not use the C++. So what's the reason you use the Kotlin?
Right. So in general, I do competitive programming in Kotlin, but for this particular contest, it's actually not a good choice. Because I'm the only person in the team that can code Kotlin, but they code C++, right? So basically, I have to code for the whole 5 hours, and it was quite exhausting at the end. And in fact, I made quite a few mistakes for the last few submissions. I did like incorrect configurations, or like I just have a bug, like many bugs for, yeah. And so our last hour didn't end very well. So it was not a good choice in this particular situation.
So how's the teammates seeing? You cannot see. Can you see the debug?
Yeah. So in this, I guess for this particular contest, that's fine because our strategy is very simple. It's just like most of the core logic is not in the Kotlin. It's mostly on the like choosing the configurations or like thinking of what other options to try. So on this side, is like the language barrier isn't very important. Right?
Okay. Thank you. Thank you. Okay. Okay, just put. Okay. Okay, let's invite the next team. The next team is Afterlife. Afterlife. Welcome.
Hello? Hello? Which one is that? Hello. Okay. So I'm going to try to introduce our solutions, and hopefully my baby English can handle all of this. I even write a script for this. Which one is the highest submission? I think it's this one. So basically, we are trying to decide whether to start a task in each second, and when handling the problem of maintaining GPU memory usage on each memory, we directly maintain all events on every GPU and simulate these events to check whether a task could be allocated to a given GPU. So this is all events in one certain GPU, and we are trying to check whether a new task can be assigned to this GPU, and by simulating all these events and check whether sometimes the memory usage is out of the limit. And for task allocation, our basic idea is greedy, that is to scan all unallocated tasks in a certain order and scan all GPUs in a certain order. I will try to find all these codes. Yeah, so the weighted list means all unallocated tasks, and it is sorted in a certain order where we try to use some different task score to sort them. And assigned the task once, we found a GPU that could accommodate it. So we both sort task and GPUs. And for task ordering, we used the total GPU memory usage as the sorting as sorting method, namely as the is quite similar to the previous team. And we also try some different usage of the scoring function, but it all runs very badly. And for the GPU ordering, we designed a score based on the remaining GPU memory and remaining task capacity and the events corresponding to the last ending task. And this is maybe the GPU scoring. And the overall idea was to distribute tasks more evenly and avoid the long tail issues. And at first, the solution could not produce results within the required time limit. So we tried to do some constant work on this code. And the most important thing is to, when we find something, when we find someone, some task which cannot assign to any GPU, and we count the number of this kind of task, and when the number exceeds some memory, we just stop the simulating for this second, and we just set all other tasks as non-assigned, or to assign these tasks in the following seconds. And this is quite important. I don't know whether it works, but I don't know why it works, but it just works, and it's improved the score very significantly. And the last thing we did is to try to adjust all the parameters and try to find some more accurate parameters for the task. We didn't figure out that we can use something like exit code to get the exact data or the hash value of the data for each test case. So we try to find the accurate parameters by our hand, and this is the final accurate and final parameter. So this is our code. Yeah, and that's all.
Okay, anyone have question? Okay.
So please go back to the 127 line.
127 line.
Yeah. So how did you decide the number 18? So what's the meaning of the bad?
The bad means in the current second. So we just to scan all the unassigned tasks and try to put it in some certain GPU. And when the task cannot be put in any GPU, we just mark it bad and count all the number of beds. And when it exceeds some, like the number 18, when it exceeds 18, we just stop the seconds and set all other tasks to be so we let all other tasks to assign in the following seconds, not in this second. And the number 18 was from by testing all the numbers. So initially it was 3, and we increased the number, and the score is increasing. So we increased until it gets 18.
Okay, so it's just by experience.
Yeah, by experience.
Okay, thank you.
Any other question? Okay, thanks, Afterlife. Thank you. And okay, let's invite the next team. The next team is Pro-Bear Transform. Okay.
Okay, so firstly we have find the hash for each case. Also we had 2 comparators. First comparator is by consumed memory, and second comparator is by the time that task, like we can have 2 bottlenecks. Either it's the consumed memory, either this running time of tasks. So it's either memory or B in the statement. Where is the second? This is the second comparator. So we are sourcing GPUs in some order. I think it's not, like, we know that in first 40 cases, k equals 4. In the next 30 cases, k equals 1. And in the other cases, k is like a big number. So, so all cases where the solution got a good score is cases with k equal 1. And so for this case, the sourcing of GPUs is not important. So we just shuffle them. Also I think, is it? It's our best submission. I think here we changed division by 2 to 0.6. Maybe if we tried with several alphas, we'll got a better score. I don't know. So, but actually it was like our implementation of baseline worked in 6.7 or something like this out of 7 seconds. So, so it was hard to push baseline by time limit. Yeah. So okay, that's all.
Okay, any question to them? Any question? Okay, I have questions that in the 122 line, you use the text hash to, it seems that it's corresponding to a specific test case or
yes,
not?
It's test case 68, it's test case 50 something, I don't remember.
How?
Like it's the test cases where this comparator got better score than this.
Okay, okay. Okay, any other question? Okay, so...
and we also used the exit code to determine the hash.
Yeah, so in the beginning it was like here, in the not previous submission, but some submission it was here exit test hash. Or here.
You try a hash to recognize the text case. Okay, I got it. Okay, thank you very much. And the next team is USA 1. Welcome.
Hi everyone. So for our team, what we did is, well, first of all, we started with the baseline, same as most teams. Then the first thing you want to do is you want to just change the formula in the baseline so that basically the tasks that are cheaper or like that require less resources overall are used first. And then, but I think the idea that maybe did not, no one mentioned yet, I think, is that, so in general, if you knew all the tasks from the beginning, if you knew the whole set of tasks that you need to execute, then instead of just going greedily, so like at every step trying to get some new tasks and like finding which task to execute at this timestamp, and then just go to the next timestamp, is not as good as if you instead try to build the whole schedule. So if there was some way to optimize the whole schedule of the thing, then you can get, at least in theory, you can get better results because you can directly optimize the objective function from the problem instead of just having some heuristic function that you're trying to optimize on each timestamp separately. Because in the latter case, it's less clear that you're actually optimizing the right thing, right? But you can, of course, experiment with different functions, but it's not so direct. Yeah, so basically, you can sort
still like store the tasks in the order of the some heuristic function, but then you can basically, instead of trying to just going through the tasks one by one and adding them to the current timestamp, you go through them one by one, but you try to add them to the earliest possible timestamp from now in the future, so that no resources are overflowing on any GPU. And so you go through each task and you just put it somewhere in the future. And then now you can take the permutation of tasks that you got at the beginning and you can evaluate it. So you can basically find the score that you can get for this permutation. And now you can optimize this permutation so that you can try to swap two elements, or you can try to take one element or like one task and move it to a different place in the permutation and re-evaluate. And if it gets a better result, then you can keep it there. So we had some code that did all of that. So, well, yeah, unfortunately it was not used. But anyway, this idea, I think in general, is a good idea because like you can, so basically what you can do is you can just optimize something every timestamp. Like when you have some set of tasks that are current and like you need to schedule them, you just build the whole schedule from scratch. And then you just follow the schedule until at some point you will get a new task, right? And when you get a new task, you can just rebuild the schedule from scratch again, and so on. And in theory, I think this is a very good approach. I think in practice, the main problem is that it's, of course, much slower than the greedy approach or any other approach, I guess, presented before. And the problem is that there were some small test cases in the set of all test cases. I think the first 50 were maybe pretty small, but I think also their influence on the score was not that big. So in the end, we didn't really use any kind of optimization like this because like it didn't give us too much score. Even if we do a bit better on the first 50 cases, I think the real like the real big points that you could get were like in the other cases which were too big for this approach. But still, I think this helped us to get the idea for our final approach, which is similar, but there is no optimization anymore. But still, the idea is that instead of trying to optimize what we are executing in this one current timestamp, we instead are trying to build a longer schedule. So I think for some reasons with like time limit balance and like the quality kind of balance. So like we eventually did something like this. So we have some kind of a variable, like I think it was like 50 or 70 time the ticks. So basically what we are doing is that when you have the order of tasks in order of their like resource needs, right? We have this order for each task. We try to put it at the current timestamp. If we can put it in the current timestamp, we just put it there. If we cannot, we try to put it at timestamp t+1. If we cannot, try to put it at timestamp t+2, and so on until like t+50. And if we can find a place in the near future, basically, when we can execute this task, we just put it there in the schedule. So basically, the greedy approach is just discard the task if we cannot put it at time t, but our approach still puts it somewhere later. And I think why this is good is basically because if you have some task which is pretty bad for you because it maybe blocks a lot of different good tasks, but it maybe for some reason still fits in timestamp t, you might not actually want to schedule it there. So the idea is that if there's a good task that you cannot do right now, but you can do it very soon, you should also account for it in your simulation. So that was the main idea in the end that we did. I think if you think about it deeply, like if you think about the approach from Dvoje proti Vetra, the first one presented today, basically what they did is when they did this greedy approach, if they had like 35 tasks in a row that they could not add to the current timestamp, they just broke the for loop. They just stopped trying any more tasks. I think it's similar in the approach because basically it's also preventing getting bad tasks from being executed at this current time, right? So I think it does it just in a different way. So it just limits the task that you are taking in this current timestamp, while our approach does not limit that, but instead for tasks that you cannot do in this current timestamp, you schedule them a bit later, which will naturally limit some bad tasks from being scheduled right now. So in a way, it's similar in the intention, but it's different in implementation. And yeah, the last but not the least is, of course, the formulas for the greedy order are very important. And our trademark formula was this. And this constant 1.594982 is very important. 1.6 is maybe 1 million points worse. But it was our last submission with 26 seconds to go. And it was a huge team effort. Basically, each of us typed a few digits in this constant. And that's how we got our best results. So that only proves that teamwork is crucial.
Yeah, it's a magic. So any questions to them? Any question? No more question? Okay, thank you. Thank you. Okay, let's invite the next team. I think the next team is Bet at DS. Bet at DS. Welcome.
Hey guys, I'm gonna share our code with you guys, and honestly, I think we didn't do much smart things like the previous groups, and we didn't identify the quadratic term in the schedule of the tasks, and we didn't do smart things on GPU scheduling, and also like we are using completely brute force on implementing the baselines. So, but I think the non-trivial thing we have done is adhere. So basically, we have a great infrastructure on testing the hyperparameters and integrating into our solutions. So we have a very small latency on trying each hyperparameter and improving the results. So we even build a local test system to like estimating our scores based on the previous performance or something. So so it enables us to try like 10 or 20, I think it's around 20 hyperparameters. And for each task, we select one that works the best. And so we have 2 hyperparameters. No, I think it's 3, I think, yeah. So the first 2 is how we schedule the tasks. So you can see we have very bad code here. So so ST means, yeah, what is ST? Oh yeah, ST means L in, and len means L out. And the TT means the current waiting time. So like this task had already waited for TTX time. So like if C2 is greater than 0, so we will mostly prioritize those who wait the most. And one of the smart things we identify is some tasks the best hyperparameter is requires C1 to be less than 0. So it's very very not very reasonable, but it's practically is. We can see yeah, we can see here like sum of the C1 is less than 0. So it turns out to work very well on some large tasks. I think you guys already know the largest task is task number 68, I think. And the best C1 works for this is minus 0.4. Yeah, another thing is here. So what we done here is we noticed that some bad tasks that cost a lot of time came very first, and some easy tasks came afterwards. So if you directly schedule the long tasks without receiving the short task, it will cost a lot of time, cause a lot of latency. So basically, what we done is to wait. Like if a task came in, we first wait until the next tick, and 2 adjacent ticks is like 50 time steps. I think it's by default, which means that if a task came at time step number 2, it will wait until time step number 50 until it's be scheduled, and then there are lots of tasks, and we can do like better optimization on this. Yeah. So that's all.
Okay. Anyone has question to him? Okay.
Hi, thank you for your solution. Can I ask like why is a TT term in the loss function? Because like in the actual scoring function, right, it's like a sum over D.
Yeah.
Like maybe if it was like sum over D squared, like the loss, like this TT term will make sense to like, but here like I don't think we care if like we swap different tasks, right? So yeah, I was wondering about the TT term. Yeah.
Okay, sure. Yeah, it actually turns out the C2 is the last thing we add onto it, and you can see in the data like C2 is rarely to be greater than 0. So I think you are probably right, but it turns out that it helps a little. So it may help from like 360 to 361, so we just did it.
Okay, thank you.
Yeah, so it's just experimentally.
Any other question?
Oh yeah, so for each hyperparameter, we submit once and get the results and copy it to local. And for each task case, we calculate the maximum.
Yeah.
Oh yeah, sure. Yeah, for the first 40 tasks, I think we have like k equals to 4. Yeah, and for 41 to 70, we have k equals to 1. Yeah, and the number of b just varies, so there's no like clear message in it, I think. But what we did on the hash function, I think is quite different because, yeah, we are not hashing on nk and b. We hash on the first task that came in. So it also has no cost, but it's really helpful that separates 100 tasks in one shot. Yeah.
Okay, any other question? Okay, thank you. Let's invite the next team. The next team is Polish Mafia. Polish Mafia, welcome.
Okay, so okay, so first it's, I guess nobody mentioned it, but I like the problem for being very non-obvious. So for example, in the statement we were given the scoring function, which consisted of like 3 summands, and the first easy but non-obvious things is to ignore two of them. And when we get to being focused only on the sum of waiting times, we had a sorting function similar to most, like we had a sort by something similar to area with possibly a few variations about it. And we also had a sorting function for the GPUs. So the problem was for each job and each GPU to check whether we can fit it in it, and to also calculate how much space will be left because we want to use it in the sort. And we were actually able to code the data structure for that, unfortunately, because we didn't get to the crucial optimization. So we had to find the crucial optimization about breaking after like 20 jobs or something. So we had to fight for points otherwise. So the main idea was to try many different scoring functions for the order of the jobs. And we obviously wanted to use the best of them on each test case, but it's untrivial because unlike in any other optimization competition, the tests are closed and we don't know anything about them. So I heard a few teams use the return codes, which is, I love this idea, but we didn't think about it. So our idea was to allocate as many megabytes of memory as the hash of the test, which also worked well. And then based on the detected test, we can apply the strategy of our choice. Yeah. We also, as Gennady mentioned, found teamwork very useful. In particular, one of the teammates was producing one of those functions every half an hour or something, and that was his input into into solving of this problem. We had some nice ideas, like at the beginning we thought that maybe it would make sense to once every now and then run the simulation on the historical data. Like if you wouldn't be able to get to know the tests and we would like to choose the best strategy, maybe after like 10% of the time it would make sense to check which strategy would be the best so far. But as we get the hashes of the tests, it didn't matter anyway. Wait, I had the notes. Let me check if I have something else to add. I guess one extra hint about writing data structures, because we had, it's pretty simple. We didn't go for segment tree. We did something binary search based, so it can be done actually. And a nice hint is to use the scoring, to use the judge, because we don't have local tests, to verify, to have two codes that should have identical results on every test, but one of them should be faster, so to not merge multiple changes, but to check data structures separately and verify if the results didn't change. And I guess that's it for us.
Okay, any question to him? I have questions that, for example, the 353 line, you use the test to identify the tech case, right?
Yeah.
But how do you know that the test? The test is the hash or?
Yeah, I mentioned that a few previous teams used the return code to return the hash of the test, but we didn't come up with that. So we calculated a hash like modulo 100 or something like that, and that's how many megabytes of memory we allocated. I think we have it somewhere. somewhere. Give me a second. Oh yeah, that's unfortunately in Polish, but it's supposed to allocate as much memory as the hash of the test, and the judging system were reporting that. Yes. No, my teammate wrote it, but I'm so pleased that you know it. Any other questions?
Okay, any other question? Oh no, okay, thank you. Okay. Let's invite the next team. The next team is we press with Mart in the northeast.
Yeah, so we use similar ideas as some of the previous teams. Like we have a function on the we have a function like calculating some value of each task that we want to give a priority of the tasks, and the function is like a combination depending on test cases. But the high level idea is that we give maybe a quadratic function on the L out, the duration, and like a linear. Yeah. So so it looks like this, and also a slight difference with compared with previous team is that we also gave some penalty on the arrival time. That this is the last term is arrival time, but this is small because we gave a like higher priority on the size of the task, right? Like we want to so we want to perform the lighter task earlier, and then then we use this greedy, and each time we check if some task in the queue can be performed by some GPU, and here we for one task, if it can be performed by multiple GPUs, we also give score on the GPUs. The score looks the score is here. So we assign the task to the GPU with the load, the proper load that is closer to the size of this task. So this is the score is so this is the load of this GPU. The load is computed using the capacity remaining divided by the remaining number of tasks it can perform. So say if there is only one slot left, then it is just the remaining workload, the remaining memory. And yeah, so you can see like in the end we just we also want to combine several functions, but in the end we don't have enough time that we just do it like very lightly, divided by k and some large test case, and yeah, that's our solution.
Okay, any question to him? Any question? Okay, no. So, thank you very much. Okay, let's invite next team. The next team is In Gan Gan. Welcome.
난 말 안 할 건데.
아니, 너만 나간 거 아니야?
내가 나가? 내가 설명해? 내가 한다? 그래. 어디 있어? 뭘 띄워줘야지. Well, I'll explain step by step. Actually, I don't know the problem as a whole. So here's a data structure. By the way, quick language lesson. 자료구조 is data structure. It's pronounced 자료구조. It means data structure in Korea. This means task in Polish language, but I always pretend that I know Polish, but I wouldn't try to pronounce it. I'll not do that. I know I'll fail, so I'll not do that. And stuff. But basically it's simple. So basically what we're trying to do here is to maintain a data structure which supports adding a task and like which supports whether we can add a task or just really add a task if given that it is safe to add a task. The time complexity here is O of B, and the memory probably likewise. So it's quite efficient. It's not the best, I guess. I guess you can do it log time, but why? And also something that is kind of important here is that this is a pair. So you see that we return a pair. Why there's another Polish language? I don't know. But whatever. So there's a pair. So this means we can add we can add this task, and the next one, the remain, is kind of a so for every time frame, if we add a task, then this is the minimum of the remaining GPU memory size or whatever. This is the minimum of the GPU memory size over the length L in times L in plus L out minus 1. So we compute that in the data structure and we will use it accordingly, basically. Something amazing happening. Okay, this is getting long. Okay, we need to know the task and we do know the task. The problem is, I don't know, the way we interacted with the judging system. Okay, why do we need to know the task? We had some strategy, something works on some tasks, and the other things work on other important tasks. So we want to take the point-wise, like test-wise maximum. So basically, that's it. And so how do we know each task? Basically, you can have 4 answers, right? Accepted, wrong answer, time limit exceeded, runtime error. So well, you can do 2 things. This gives runtime error. This gives time limit exceeded, right? And I guess this gives you a wrong answer. And these are based on the hash of the determined values of the input, like the non-interaction part of the input. And so with 6 submission and a good parser, which we wrote separately, but you don't have it here because it's in local. So we wrote a parser, and from there we can infer the test number. And from there, we have certain strategies, and we just actually compute the score, which is also from the parser, and we'll set our strategy accordingly. So what is the strategy? So the strategy, the way strategy differs is the sorting order. So given the sorting order, how do you perform it? Given the sorting order, how do you perform it? Actually, I'm not sure. I think my teammates will tell you about it.
The sorting order is, I think, mostly similar to other teams. It's L in times mod1, which is coefficient, plus L out times mod2, which is also coefficient. And also there's another strategy that is about the area that the the task fills. So there's one strategy for just linear and one strategy for quadratic. And there's about 7 strategies, and we just did pointwise maximum. And yeah. And yeah, we got the pointwise maximum, and we got the score. Is there something? Yeah, it's just greedily fill the task. That's it.
Okay, any question to them? Any question? Okay.
So I have questions about your parser. So from your previous experience to attend other UCPC or other ICPC challenge session, so is it a usual way to use a parser to generate this large volume of kind of parameters or magic data? So because our challenge problem is from a real business scenario, so we simulate a online inference system, so with randomly arriving large volumes of requests. So I'm trying to understand whether it's a usual way to use this kind of technique to resolve a UCPC challenge problem.
I don't think usually we can see each score for each test case, so I think this is one of the specific case. But since there is an obvious advantage to separate each test for this kind of submission, so I think we just take that strategy for this problem, especially.
Okay. So the reason I think is because of the distribution of the requests is just unidentifiable. So you don't know any statistics of this large volume of requests. So you use the parser, try to generate the parameters and the hash number. Am I right?
Well, I guess my take is that, well, first of all, I don't do a lot of challenge. I don't think Eintal also does a lot of challenge either. So whether this is a normal thing or not, we are not in the capacity of answering it. We don't know we're programming contest participant, so we have no idea. The second thing, whether this is normal, I guess no. And I think the challenge problems we have participated usually just gives you the test data. So this, I mean, taking the maximum of the strategy should be quite obvious in most of the, like at least the subs that we did. Like for example, hash code. I think there it is just something we can do. But here we cannot do it. And if we do it, it was adventurous. So we should do it. Yeah.
Okay. Thank you.
Any other question?
What? Wait. Could you? Good question. Well, you gave me a hint. Scopo? Well, I would say like Scopo, something like that. I think. Scopo. Wait. Okay. This is why I don't attempt to pronounce it. I actually did, but like at some point I realized that all the pronunciation I knew was all wrong and stuff. Yeah. Well, I mean, I sold a lot of POI, so I guess, yeah. Yeah.
Okay, any other question? I thought you had generated so many magic number during the call. Is it totally random or random by some strategy?
The list of the numbers you have seen is not magic. These are the result of these are the verdict of the submission that we had. We had a parser to translate it as a score list. So we don't have a magic function. The magic function we have is just this. Just these 5 steps are the magic functions we have. There are some sort of trade-offs here, but, well, yeah. This is all the magic constants we have, I think, yeah. And these are just like fractions, yeah.
Okay, another question is just now you have said when we arrange a task into a specific GPU, you say the first time frame is the minimal memory usage. What do you mean the minimal GPU memory usage is for this task or for the whole GPU?
Oh, so, that means if I assign this task to this GPU, then there's some time frame that have minimum memory remains. So it's like tight. So we want to make GPU tight. So yeah. So fill the most.
The rest GPU memory.
Yes, that's the least remaining memory.
Okay.
For that
Thank
type.
you. Okay, thank you, RBU. Thank you. Please take a seat. And there is all the teams we have invited. So if any other teams want to be a volunteer to share your code, share your idea, please raise your hand. Okay, thank you. You can introduce yourself first.
Okay, so I'm from team Homo, and we, I remember that we did pretty well in the first hour and then failed badly. So that's why we didn't want to give a speech. But I found something only one our team did. So let me explain it. So it's so during the testing, we found that at the moment we receive all the end requests, 90% of the requests are not assigned. So which means 90% of the problem can be solved in non-interactive way. So I just split the problem. So in the interactive phase, I did a similar thing to other teams, and after reading all end requests, I solved it in a different way, which is a kind of batch function, which means we have all the remaining requests and solve it assuming there's no further requests. And the advantage of this strategy is that you can try several sorting functions, which means so I heard some teams are trying to guess the hash of the test case and switch several sorting functions, but in this strategy, in our strategy, you don't have to do that because you can, since the problem is not interactive, you can just try to solve it with several sorting functions and just take the best one, and that's what we did. Yeah, so, and the inside of the batch function is kind of similar to other teams. We just use several sorting and assigning sorting requests and assigning it greatly, and the sorting function is kind of like this. So just a linear combination of out and in time, and what we change by it is the weight of these two out and in values. And I think these are the coefficients of these two variables. So I run several batches with those parameters and take the best one. That's all what we did. So thank you very much.
Okay, any question to him? Okay.
Excuse
Sorry,
me?
maybe.
This 90% being documented, was it happening in this 20 important tests with k equal to 1 or in the other tests? So sorry, I didn't hear you.
This 90% thing that you mentioned, this static problem, was this occurring in those 20 important tests with k equal to 1 or in the other tests?
Actually, we didn't know the value of k. We didn't try to guess it.
I meant from 51 to 70.
No. I mean, if I remember correctly, I submitted a solution. There's assertion that when finished reading n tasks, if the number of finished tasks is less than say 10% of the tasks, pass assert and otherwise abort or something. And if I remember correctly, almost all the tests passed. So that's why I thought that switching to static problem would be better, and actually it worked. So, but I could be wrong. Yeah, but some tests failed. So yeah, but I'm not sure which test was that.
Okay, any other question? I have a question that I had see inside the code. You have a comment that there CF problem.
Yeah.
I have saw a comment that say indicated CF. Is a template or?
I think it's a template.
Oh, it's a template. Okay, okay. Any other question? Okay, thank you very much. Thank you for your sharing. Any other volunteer here? Okay. Any other volunteer? It is the end of the Roadshow section. We can take a break. That pay attention. We will the close ceremony, the award ceremony, will begin in 15:15. So pay attention to back here before 15:15. Thank you very much. See you later.
I've started my comparative programming journey when I was a junior high, and my first aim was to win gold in IOI. Then when I entered university, my goal was to win gold in ICPC.
I think I've started competitive programming at around like 2011. I won ICPC World Finals in 2018 and 2019.
参加这个 UCup 对我算法竞赛有很大的正面影响，感觉题目质量都比较高。
小学的时候用那个 Scratch 编一点东西，觉得电脑很好玩，想要干点这个，然后就选了一个有这个信息竞赛的中学去上，然后就开始这。
And I started doing them actually quite a while ago, which is 15 years already.
I'm the youngest. I'm doing competitive programming for 11 years. At some point you come across like a branch of math, which is programming, and you decide that it's interesting, it's nice, you try it, and maybe you discover that you are good at it.
I've been doing competitive programming for quite a while now, since I was 7 or 8 years old. I started mostly because my parents are programmers and they just felt like, I mean, I was probably good at math, but I wasn't doing math Olympiads, of course, but they decided that like I can try and like see what goes.
I started competitive programming in my 3rd grade of the high school. I study statistics at my university, and I have interest in finance, so in my future I will study about finance more than programming, but I like to do competitive programming because puzzle and mathematical things of this is very fun.
接触算法竞赛大概就是初一的时候吧，就开始写游戏，然后就顺便学了学编程。
I think ICPC teaches you how to solve problems in general, like problem solving skills, and also how to do things fast, even if, for example, you're doing coding interview or just doing work at work. It actually, I think, indirectly helps you, and I think I observed some cases where I think people could have benefit from having some sort of background like I have.
Yeah, and I do think that competitive programming experience helps you to like go faster, to like create some like starting point, to like create some code quickly and to get it working. Also, it helps you to be like more careful with like some corner cases, because you in competitive programming you want your code to like always work on all test cases.
I just enjoy problems. Of course, I enjoy winning, but even if I can't win, I still can enjoy computer programming. So I'm involved in this community.
One definitely important thing is that competitive programming problems are challenging and they are like being progressively better at them. I think performing under pressure is another factor that can become important in life at various points.
And I think it's generally competitive programming experience is rather useful for high frequency trading, because like you want to test a lot of ideas and you want to do it quickly, and that's precisely what is like really good, what competitive programming trains you to do.
就我觉得我从竞赛中学到一个教训，就是其实有的时候合作非常非常重要，就是你和人聊一聊什么，其实对你会非常有启发。
Pure joy of solving just problems and work in the team. So now it's an on-site event. I'm really happy to be here, because usually even in a team, we participate in contests remotely, and it's not the same experience.
But anyway, I think a lot of engineering skills indeed, like there's a lot to gain, and especially like if you are looking for like different ways to do it, like I think you can learn a lot from other people. And for example, often when you do competitions, you can learn the approaches of other people, or like how they handle their like code or like ideas, and that's very valuable.
I will just stay close to just theoretical research.
I'm now working on Kotlin programming language compiler. I'm quite happy with what I'm doing and don't have any plans for big changes?
I did a research master's degree just right after my ICPC last event, so that possibility to return to, I didn't get a PhD.
就是做理论计算机，经常想题，挺有意思的。
然后读人工智能的专业对口的博士，对，我做的是可解释性方向，也是读人工智能方向的 PhD。对，然后做的我也不知道做什么，可能还在探索。对，但我也很想造出来更聪明的模型。
Well, I work in physics. I'm an experimental physicist.
I am a bachelor student, and right now I really want to keep studying and pursue a master's degree and maybe something even further.
我未来计划继续打 ICPC， 就是这方面的竞赛，争取能到 World Final。然后我也会继续练习。
For me personally, it would be cool to be on the cutting edge of technology.